So we are at the tail end of talking about various current configurations that cause various magnetic fields. We did two last time, the infinitely long straight wire, which is kind of a workhorse one because you can find the magnetic field anywhere you want. We did a circular current loop, and we talked about what's the equation for the magnetic field just in the center only, and then that's the only place where you can find it quantitatively. And then finally today, we'll talk about the last one, which is a very long tube of such current loops called a solenoid. And then we'll talk about bar magnets. So one of the things that you may, of course, have your experience with magnets or most early on, playing around with just bar magnets. We'll talk about how does that kind of factor all in. Okay? So let's go ahead and get started. I showed you what a solenoid was last time, but before I just throw that down on the board, I want to get to what its field looks like with an analogy. So what I'm going to do is I'm going to separate the board here into a top half and a bottom half. And I'm going to put stuff up here which are familiar electric fields, things that we've talked about. And then down here, I'll put kind of the analogous thing with magnetic fields. So, first things first, I want to start off with an electric dipole. So we know that, so let's put this down. I'll put a plus over on here, and then a minus over on like that. We call it an electric dipole. It's equal and opposite charges. So we know that charges make electric field, and now I have two charges. That's why it's called a dipole. I guess I can label this. This is the electric dipole. And let me remind you what the field looks like of it. This is the one that we sketched the electric field map of when we were learning to sketch electric field maps, so hopefully this doesn't come as a complete surprise. It looks something like this. Kind of has this like general lobey shape, okay? Let me draw for you what would be kind of, to me, the most analogous magnetic field formula, or the magnetic field. I'll draw that current loop. And this we drew the magnetic field of last time. We said that going out the center, it goes in the same direction as the normal. And then it kind of wraps around like this. We sometimes even call this a magnetic dipole. Now you may ask, where are the two things, right? Where's the di and dipole? Where the electric dipole, we literally have a plus and a minus charge. What is there two of here? Well, it's going to turn out that there's two things called a north and a south pole. So a magnetic dipole, it has two poles. I just haven't quite showed you where they are yet. We'll get to that in just a moment. So that's kind of my baseline, and then I'm going to kind of to stretch and warp what I have going on here to form different looking things. For instance, remember in the electric dipole, we imagined that these 2 point charges were kind of like little lumps of Play-Doh, and we're going to smash them and going to spread them out. One of the things we did was we smashed them into small plates like this. this was what we call the finite parallel plate capacitor. So what we found there, and this, I think you did this in your electric field mapping lab, you actually plotted and found that the electric field was pretty close to uniform between them, and then started to have this kind of lobey shape on the outsides. Oops. Etc. And the finite cap was kind of the missing link to when we eventually not only made these flat plates of finite size, but took them out to infinity. So we now talk about the infinite cap, where these plates never end. Just keep on going. And if you look back in your notes, what we have found that gives us the advantage of extending the uniform field between them out forever. So at this point it becomes perfectly uniform, just going out forever and ever. And one of the strange things we found was that the electric field on the outside was zero. So this is all in your notes from before. So I'm going to do the same thing with my magnetic dipole. I'm going to start morphing it from a single loop, or maybe a very few couple loops that can all be imagined to be in the same place, to a finite tube, to an infinitely long tube. So let me do that. So here's a finite solenoid. So we're going to take a bunch of these loops, like so. And same deal, if we draw the magnetic field of that finite solenoid, the effect of making it a tube is to kind of make the field look like this. I'll draw a dotted line when it's on the inside. Etc. Sorry, that's not the best drawing I've ever done, but hopefully you can see it's kind of like the extended version of the magnetic dipole, right? So what you start to have is that the magnetic field pretty much points to the right inside, and then it loops around once it gets out. So you can see that it shares the same features as up here, right? The finite cap, when you're between the plates, the field is relatively uniform and it starts to wrap around on the outsides. Well, this is relatively uniform in the interior, and then it wraps around when it gets out of the tube, okay? So by not having it just be a single or a couple turns, but starting it to have it be a significantly long tube, we are going to have a situation in which the field is approximately uniform. So what do we do next? We just make it infinitely long. Infinite solenoid. So we take this tube, let me get a better marker here. This tube goes on and on forever. Well, it's highly analogous to the infinite cap in the sense that what is approximately uniform in the interior becomes exactly uniform. So the magnetic field in the interior just looks like this. And on the outsides, it's zero. Basically, the magnetic field lines can't wrap around because there's no end of the tube to escape out of to wrap around. So we went from the electric field being relatively weak outside the plates to being zero completely. Now same thing here. We went from the magnetic field being relatively weak outside to being completely zero. So there's my motivation for why the infinite solenoid has the field characteristics that it does. It's, once again, some kind of strange infinite geometry to get the simplest field possible, a uniform field. To get a uniform field, we needed an infinite plane, or a 2 in this case over here, and same thing over here. We needed some kind of infinitely long tube. So, let's talk about the formula. We know the formula for this. For the magnetic dipole, we said that we can only find the magnetic field in the center because it's certainly not uniform, and I give you this equation. And I said, don't use it if the number of loops gets very large to where you can't imagine them all being completely in the same place. But you can see that that formula is not going to work when we extend it out to a tube. If we make n equals infinity, because we have an infinitely long tube, that's going to blow up. So for the infinite solenoid, I'm going to have to tell you what becomes of the math. And here's what it is for the solenoid. For the infinite solenoid, we have to talk about the size of the magnetic field and its direction. And I'm going to have to just tell you what the formula is. It's not in the scope of this class to tell you how to get these, although they all of these come from relatively few simple laws. So the direction, that's easy, because it's the same for a bunch of loops as for one loop. It's the same direction as the normal vector of all of these loops. All of these loops have a normal vector that points to the right. And the size of it, well, I guess I should split this up. Inside versus outside, I should remember to state that outside it's nothing. Okay? So what we're finding is the magnetic field on the inside of the solenoid. Here's the equation. Mu naught Ni. So that's it. Now this lowercase n, not uppercase n, but lowercase n. Lowercase n, that's not normal. What that is the number of loops per length along the solenoid. It's basically the turn density. It's how tightly is the solenoid wound. So the units of this are actually inverse meters. For instance, lowercase n, it might be 100 turns per meter. And that is not as tightly wound as something that has 500 turns per meter. So literally what you do, you can't of course talk about the total length of an infinitely long tube, but you can still talk about it. Over a length L, there'll be a certain amount of turns. 1, 2, 3, 4, 5. That's 5 turns per whatever length, right? So it's a turn density. And you can see if the solenoid is more tightly wound, that will increase the magnetic field. That hopefully makes sense, because if you're more tightly wound, you'll have that much more current near any one spot, right? And the other interesting thing is that there is no factor for where you are inside the tube. This is a uniform field. That is the magnetic field everywhere inside the solenoid. You don't have to say if you're at the middle or close to the edge or whatever. All you have to do is say, well, I'm inside a tube, it has this turn density, and the current running through those turns is this, and this is the field then I'm going to experience. Okay? Are there any questions on this? All right. So we are ready, I think, to move on to magnetism and matter. So bar magnets and things like that. What's going on there? How do they work? Okay. Are there any questions before I do that? Is there some space? Okay. So, yeah. I wish I could keep these up, but I'm going to have to clear a little space. I might have to draw one of them later on. Let's talk about magnetism and matter. So here's the thing. What you need to know is that if you have a good old electron, right, one of the fundamental particles of matter, it has a bunch of properties associated with it. One of which, of course, is its mass. Mass is the property of the electron, and it tells you how it interacts with other masses, and those interactions are called gravitational, right? So gravity is the club of masses attracting other masses. Okay? So I guess I can put here, the top row will be the property of the object itself, and then that leads to an interaction with other things. Mass is the property of the electron, which talks about its gravitational interaction. We also, of course, talk about its charge. So charge is the property that's assigned to the object to account for what kind of interaction? Electrical force. So there is another one. I'm not going to tell you how it's defined, but there's a magnetic property of an electron, and that, of course, enters into magnetism. So an electron is like a tiny magnet in and of itself. Okay? And that will lead to magnetic effects. Now, if you ask, how is it that an electron is a tiny magnet? Well, that's like asking, how does it have mass, or how does it have charge? These are just things that's true. Okay? And so what we're going to say is if these most fundamental particles have these things going on, let's build it up into why is it that we can see magnetism on an everyday level? Why is it that you can stick a magnet on your refrigerator? Okay, so we have to figure out how it gets all the way up from electrons all the way up to our daily lives. So let's figure that out. Oh, and by the way, if you wanted to, you could even put down the magnetic field made by the electron. It would look like a little dipole, little magnetic dipole. It would look something like this. It would have a little normal vector like that, and the magnetic field coming out the center would be like that. And you look at that and you go, huh, okay, that seems to be the exact same magnetic field as a current loop. So if there were a current loop, it would look like that. All right, here's the normal vector, here's the magnetic field. So the logical question is there a little current stirring around inside an electron? Well, here's the answer. Nobody knows, okay? No one has any idea if there's any kind of internal substructure of an electron. As far as we know, there's nothing, we don't know what is going on inside an electron at all. But we do know, even if it's a point particle, that it behaves as if it's a little magnetic dipole. Okay? So there are, of course, scientists trying to figure out what's going on inside an electron, but we're just going to go ahead and say, we don't know why that is, but what are the consequences? Okay? So every electron has its own magnetic field, has its own normal vector. It's its own little magnetic dipole. All right. So we have started on the individual electron level. So electrons, that's where we start. We have magnetism. Well, electrons are in atoms. So let's ask, does an atom have a magnetic field? Well, it depends. Here's why. As you probably know from chemistry class, you fill the electrons in these energy levels, right? Does this sound familiar? Right? You put, when you get to anything in the periodic table above hydrogen, there's more than one electron, and they fill in these energy levels, right? So on the atomic level, you have atomic energy levels, and oftentimes use some highly just some weird bookkeeping things. Like, for instance, in chemistry, what I remember is you just have a bunch of blanks, and then you imagine filling the blanks, right? And so you put in one electron like that. You might call it spin up. What does that mean? It just means that this is kind of like electron spin, right? This is the normal vector is like electron spin. It's not really spinning per se, okay? It's just we're pretending that there's something circulating. We have no idea if or what that is. So hopefully your chemistry instructor has conveyed to you, when you say electron spin, you don't really actually mean the electron spinning. There's this point particle, as far as we know, there's nothing to spin, okay? So this is what we call spin up. The normal is pointing up. So very oftentimes the next one comes in with spin down, and what that means is the magnetic field is going to cancel, right? Whatever magnetic field one makes, you put another one, it's going to make the opposite. So if you have only these, the magnetic field of the atom would be 0 if you only had these, because of the way the electrons fill. So what you've done is you've killed the magnetic field for the atom overall. Even though all the individual electrons are little magnets, the atom as a whole doesn't have one. So many atoms, they have that, and so the atoms themselves aren't magnetic. What you have to have is a bunch of electrons that all fill in the same direction, so rather than killing the magnetic field, it reinforces it. So there are certain atoms that their electrons are filled that way, and then what we have is a bunch of normals in the same direction is supernormal, okay? So atoms that have those properties, they have a lot of unpaired electrons. Those will be magnetic, okay? So in order for the magnetic field to survive from the individual electron level to the atomic level, you have to have certain types of atoms. So there has to be some coordination of the energy filling. Otherwise, that puts magnetism dead in its tracks, okay? Question?
Is that why like aluminum typically isn't magnetic?
That's exactly right. And a lot of this stuff on the periodic table, the rare earths, they tend to be very magnetic. It's because they're filling many, many levels because of the way the energy filling works. It makes more sense for them to all fill like this before they then get paired up with the other ones. So now we're at the point where the atoms themselves are still magnets, but that still doesn't mean you can get a bar magnet, because even if the atoms all are individual magnets, maybe a bunch of those won't be, okay? So here's what you can have. You can have, let's say we have an atom that has one of these, it has a kind of a supernormal, right? It's a supermagnetic dipole. Let's take a block of material. like this. And the magnetic field of each atom itself is not zero, so we've been able to get the magnetism to survive to the atomic level. So I'll draw in these supernormals. Maybe this atom it points like this, maybe this one like this. But here's the problem. The atoms are not coordinated with each other. And so what happens is that the magnetism of the material overall is still zero, because the atoms are not coordinated in any way. Atoms not coordinated. Okay? So even if they're coordinated for each individual atom, we still have to achieve some kind of group of atoms. So groups of atoms need to be coordinated. So you can see that there's a lot of coordination involved here to make sure that what is true for an individual electron is going to survive all the way up into these groups of atoms. So how are we going to do that? Well, let's go ahead and coordinate them. Let's make all of these atoms somewhat, or at least a good group of them, coordinate. Here's how I'm going to do it. I'm going to apply an external magnetic field as a coordinating agent. So we learned, of course, that if you have a normal, it really wants to align with that field, right? It'll torque until it is. That was the same principle behind the ammeter that I showed you the other day, and the electric motor, right? So if they're not coordinated, what we're going to do is coordinate them with a B external. So then it looks like this. So they all torque until they're aligned with the external field. That's how we learned that normals like to torque. Okay? They won't pendulum forever because there's enough friction to kind of get them to settle down, right? So it's like a pendulum, a real pendulum, right? It won't go forever. It'll eventually settle, right? So now, what do we have? We have that these normals are all coordinated, and we know, of course, that the magnetic field will be made in the direction of that normal. So the magnetic field will look like this now. The thing that it's closest to in my earlier drawings today is the finite solenoid, right? So I basically almost kind of created like a tube, although of course it's not tube, it's now a solid block of material, where the magnetic field comes out and then wraps back in. Did you have a question?
Yeah, I just wondering why if one is running like that?
Because the external field is this way, right? So remember, the normals want to align with the field.
Or is it not aligned?
Yeah, these are the normal vectors of the atoms. And I should mention, of course, this is a bit of an exaggeration. It's not that every single last normal will be able to align, but a vast majority of them will be, okay? So now we have a magnet, okay? So if you're able to coordinate from here to here to here, we can get this magnetic phenomenon, which was originally born from the fact that each electron is a magnet. But there are several twists and turns where we can ruin that, and we have to make sure to keep the coordination all the way up to the macroscopic scale, right? We can either have it not even survive to the atomic level, certain atoms, the electrons, the fields will all cancel, but then even if we can get each individual atom to be a magnet, they may not coordinate, in which case you need to coordinate them. Okay? So, now we have a magnet. We give names to the two sides. The side where the magnetic field emerges from the material is called the North Pole. That's where the magnetic field lines come out of the material. And the South Pole is where they go in. Okay? So, outside of the material, the magnetic field lines point from north to south. So they come out of the North Pole, go into the South Pole. I do want to, however, point out that inside the material, they close the loop, so they actually go the other way. So inside, they go from south to north to close the loop. So, of course, you're not normally inside a magnet, right? Literally inside the material. Can't get in there. There's material to block your way. You're normally sitting outside a magnet, and then the magnetic field will point from the North Pole to the South Pole. Okay. So, let's talk about this. First of all, it's very common for north and south to be thought of, okay, north and south, that's kind of like plus and minus charge. But there's a big difference between them. And one of them is it's perfectly fine to have a plus charge all by itself and a minus charge all by itself, but north and south, they stick together. You can never have one without the other, okay? So you might say, well, what do you mean? Can I just chop this magnet in half and take away the North Pole and take away the South Pole? Well, what happens if you chop it in half? You have this. This was your old North Pole, this was your old South Pole. But guess what? You just made two new poles, okay? Because the magnetic field of this now looks like this. And the magnetic field of this looks like this. Oops, that's the wrong way. So in place of it, you now have a new North Pole here and a new South Pole here. You cannot ever get one of the poles alone. So north and south are always in pairs. There is no such thing as, we call it, in normal circumstances, a magnetic monopole, which is a single magnetic pole all by itself. Mono, single. Okay? So there is no such thing as this. There is no such thing as a single magnetic pole by itself where the magnetic field lines just start there and go outward. There is no such thing. There's some interesting theoretical work. Maybe these existed in the very early universe where the laws of physics were very different than what we have to adhere to right now. But as far as we know, that this is not a common occurrence. This, in fact, is not allowable. Whereas if you talk about just a positive charge, of course, there's nothing wrong with having just one positive charge without a minus around. Okay? That's perfectly fine. This is fine. So one of the consequences of this is that if north and south poles always appear in pairs, what that means is that magnetic field lines always form closed loops. Magnetic field lines always form a closed loop. They always loop around. They come out of the north, go into the south, and then close the loop inside the material. Now, I haven't always drawn it as a closed loop. The infinite solenoid, I showed it as uniform, so maybe a better way to put it is there are closed loops, possibly of infinite size, which is to say you can never see the end of a field line. You can never see a field line just suddenly start up or suddenly end. It's perfectly fine for a point charge. The electric field line starts off here and then goes out. So instead of saying it always forms closed loops, sometimes we'll see something like this. But of course, the assumption is that goes on and on forever. You can't see the end. So you can't see the end of a line. You can't see where a line starts or ends. They always go on forever in both directions or form a closed loop. That's our way of saying that there's no magnetic monopoles allowed. All right? Okay, so that's a little bit about magnetic field lines, but now let me get back to what I was talking about before. Let me show you this process. I have here a little bit of a demo. So here's what I have. I have a block of material that is in here. That's what I'm going to magnetize, so to speak. Right now, all of its atoms are magnets, but they're uncoordinated. And so this cannot do anything. If I put a few paper clips on the table here, it can't pick them up. It's not a magnet. But I'm going to magnetize this material, and how am I going to do that? Well, you can see I've got a nice tightly wound solenoid around it. That's what's going to do the magnetizing. That's going to be the external field here. So obviously I have to send current through it. So I'm going to do that by connecting this wire to a battery. Okay? So current's going to flow around like this. It's going to make a magnetic field through the core of the solenoid that goes like this, and that's going to align all of the things with a pole, magnetic pole right here. So let's try it. Okay, so now I've magnetized this thing, and it becomes a magnet. Okay. Now, if you want to question, oh, couldn't that just be the magnetic field of the solenoid itself? Well, let me go ahead and remove the current. So now there's no current flowing in the solenoid. The magnetic field of the solenoid is off. I've taken the external field away because once it does this thing in terms of coordination, then the atoms will stay coordinated for a while. Let me leave it here. We'll see how long it can last. So once you've coordinated them, you can take away the B external, and this will remain a magnet. The question is just, how long can it last? Well, this is where I mentioned a few pieces of terminology that I can just touch upon them. Oh, and I forgot to mention here, for those of you that might be skeptical about chopping magnets in half, let me point out that even if you chopped it to a single electron still has a north pole and a south pole. Okay? So you can't get those things apart. So the two types of magnetism are ferro-magnetism, P-A-R-A, and ferro-magnetism. There are others, but these are the two that I will mention. And the main difference between these two, you may I'm not going to get into the details of why this is, but the details here are just a matter of degree in terms of how easy are they to magnetize and how stubborn are they to stay that way once they are magnetized. So the ferro-magnetism is something where if you apply an external field and then you remove it, they re-randomize almost immediately. Okay? So here, this is not very stubborn to stay magnetized. If you remove the B external, the magnetization is basically gone. They re-randomize very quickly. So that's not really of much use. In fact, this is not something that you really can even see in everyday life. Okay, paramagnetic materials don't know as much of an effect. But there is a class of materials named after one type of material. What is ferro? What does that mean? Iron. Where it's a strong effect that stays I should say, maybe use another word, let me say it's a strong effect that persists for a long time. For a long time, I should say can persist for a long time after the external is removed. So any experience you've had with magnetism is probably due to one of these very particular materials that exhibits a strong effect. So out of all the elements in the periodic table, there are only a few of these, okay? So that's where if someone is willing to magnetize it, it will stay a magnet for quite some time. You can see that in my demo here, this being a block of iron, it's staying magnetized for quite some time. So I guess we should talk about how could it get unmagnetized. Well, there's lots of forces of randomization out in the world. One of the ways you could take these and get them back into this, you could literally hit it really hard. Just shake them all up. Okay, that's one way. So I'm not banging on this thing so that the magnetization can persist. But another thing, even if you're careful with it, there's another way that things get re-randomized that you can't have any control over, and that's temperature, right? So re-randomizing things, re-randomizing influences, you could literally shake it, or temperature, right? That's what, if something's at a high temperature, it's like wiggling the things around, and they'll wiggle back into random orientations after a while. And so what you find is that if you heat anything up to high enough temperature, it can't hold a magnetization anymore. Does that make sense? Right? So the moment you take away B external, the high temperature will shake all those things back into a random orientation, and it'll lose its magnetization. Okay? So shaking is one thing, but high temperature is another thing that will tend to be the enemy of a persistent magnetization. Okay, any questions on that? Yeah?
How does the paperclip actually feel the force?
Yes, so that's the next thing.
Okay.
One of the things we talk about, right, if you played around with magnets as a kid, right, you know that north repels north and north attracts south and things like that. So the question is, how does that all work, right? That's actually going to be one of the last things we talk about, because we're going to need to bring all the knowledge that we've developed to bear on understanding that seemingly very simple thing. Okay. So that's actually probably the very next thing I need to do. Are there any questions before I do that? Yeah.
Are you about to talk about magnetizing something with another magnet?
This could very, very well be from another magnet, right? So this field could be, like if, for instance, if you looked at this field right here, it's basically going straight like that. That could be this field, right? So this magnetic field could be from any source, but it could be from another magnet. I use the solenoid, but you could use another magnet as well.
One more question. Somebody told me that when you're magnetizing another piece of metal with a magnet, you should stroke it. Is that true?
Well, yeah, basically what you're trying to do is you can't actually pass the one magnet through another, so you're basically just, so if you, for instance, if you have one magnet that you've already got magnetized, ideally you could put another magnet inside there, and that would be the best way of applying a uniform field, right? The field of the one on the outside would look like this, and then it would align all the normals of the one on the interior along with it, right? It would align them like this. Well, you can't actually put it inside, so the best thing is to stroke it right on the outside. Okay? Does that sort of make sense? No? So imagine that you have another magnet on the inside here which has random orientations, right, that you want to magnetize. The best thing would be to put it right into the core where, again, the magnetic field is uniform pretty much, and that would align it, all these normals, with the field. Right. So you can't actually put it inside, so stroking it on the very edge is the closest you can do. So instead of doing that, you do that. Question?
Yes. Does the object have to be solid, or it can be liquid? Or?
No, you can magnetize anything. For instance, if you had a piece of something that looked like this, if you put all the normals like this by applying a field, then the North Pole would be over here and the South Pole would be over here.
Does the state change affect the magnetized?
So what change? The state change?
State change, like liquid to solid and solid to.
Well, you can magnetize. It doesn't have to be a solid. You can magnetize a liquid as well. The problem, of course, with liquids and especially gases is the fact that everything's flying around, so it's hard to keep it in a particular orientation.
So if the solid is kind of magnetized, then if I shoot it out, say the liquid is magnetized, then if I cool it down, then it'll be like a solid, right? Then will it be still magnetized, or?
If you kept the atoms in their orientation as you cooled it down, yeah.
Okay.
Okay, so let's talk about attraction of magnetic poles and stuff like that. Now, before I even do this with magnets, let me do them with something that's just more familiar from the last couple of lectures. Let me suppose what I have is a current loop. Let's say like this. Now, one of the things we talked about, and this is going back to I think one of the very first lectures on current loops that we did at the very beginning of that lecture. So we talked about the fact that, okay, if you apply some external field, there's no net force on it, but there may be a torque, right? So the way we think about whether or not it torques or not is this idea that we look at the normal vector of the loop, which looks like this. We check if it's aligned with the field. In this case it is, so does it experience any torque? Nope, no torque. So the torque is 0 because the normal is already aligned with the external field. And the net force, of course, is 0 because it's a uniform field. That was usually the case for us because, of course, we wanted to focus on the torque aspect. We didn't want the loop to kind of be picked up and taken over there. We just wanted to look at it rotating in place. All right. Well, let's relax that restriction. Let's have the field not be uniform. So this is your external field. And let's put in that current loop over here again. And we talked about the fact, well, the normal here, that's still aligned with the field, so there's no torque. But now the net force isn't 0. We found that if something is in a non-uniform field, it actually experiences a net force in the direction of stronger field. So it's a non-uniform field. Which means that the net force is toward the stronger field. It will feel a net force like this. If you don't believe me, we can try it out using the good old slap rule. Okay? So let me try it. You'll have to use your imagination a little bit to think that the current at the top here is coming out of the page, right? And the current at the bottom of the loop is going into the page. I'll do it over here as well. Out of the page up here, into the page at the bottom. Let's slap that current into the magnetic field. So I comes out of the page, and I have to orient my palm so that I can slap into the B, that's to the right. So I slapped into B, force is up, okay? So the force on that current is up. See that? I, out, B, force is up. And same thing over here, right? Just the current's opposite, so the force will be the opposite as well. Okay, so looking at that, is there a net force? No, no net force. So we knew that. It was easy to remember, right? No net force when you're in a uniform field. The force, remember, that comes out perpendicular to both, right? So the force is perpendicular to the magnetic field. Well, what happens over here? It's a little bit of a diagonal slap, so it's really handy to remember that the force comes out perpendicular to both, right? Looks like this. And because the magnetic field is kind of not going directly to the right, but kind of splayed out a little bit, the forces also kind of go out of alignment. Now looking at these two, do these forces cancel? No, which way is the net force? Just like we said, right? Hold in the region of stronger field. These will have vertical components that cancel, but components to the left that reinforce. Okay, so we've basically established something we mentioned since the first, this was in my intro to current loops. I said, well, if you have a current loop in a non-uniform field, that's going to be annoying because the net force is going to be 0 as well, so let's not deal with that right now. Let's put it in a uniform field so we can focus on the torque, right? So what does this all have to do with magnets? Well, these are magnets, okay? So let me put that on here and try to show that to you. Well, we know that the magnetic field comes out along with the normal, okay? Remember that the magnetic field of the loop itself points along the direction of the normal. So there's your north, and there's your south. Okay? Over here, here's your north, here's your south. All right? Well, a uniform field is more the exception rather than the rule. As we learned, typically the fields are not uniform, right? What might be the cause of this external field? I'm going to say it's another magnet, and the North Pole is here. So we have just figured out why north and south attract. So this could be the North Pole of some big magnet, and this is the South Pole of the other one, okay? So if you understand why current loops experience torque and net force in a field, well, that's the same reason why magnetic poles attract. So let me draw you a picture. So here I have a magnet. This is a big magnet, north, south. The magnetic field over here is like this, and then of course it just keeps going. Loops around. I won't bother to draw it on the inside because we can't get in there anyway. So on and so forth. So let's say we drop in another magnet into this region. Well, if we dropped in, for instance, something like this, where the normals were all like that, first things first, it would torque until the normals were aligned, right? So that would go into this orientation, right? So its normals would want to align with the external field. Well, of course, remember, this was a magnet itself. This was the North Pole, this was the South Pole. So look at how it's just aligned. It's just aligned so that this South Pole and this North Pole are closest to each other, and this North Pole and this North Pole are further away from each other. That is simply the nature of the torque. But that's not the end of the story. Let me pull out some magnets and show you, I guess. So here I have two magnets. Oh crap, they're taped together. I guess I'm going to have to split them apart. Does anyone have anything?
Yeah, probably.
Actually, I can just make these. Or use a pen. Oh, that was Bill and the pen.
Prof. Koskelo.
Oh, I got it. Thanks. Okay, so here we have that magnet. It's got a North Pole and a South Pole. Someone's been nice enough to etch them there. And then we have another one, which the writing's really faint, but there's a North Pole and a South Pole, so I'll put them the same way here. Okay, so this one will stand in for this, and this one I will put in like this. And what we find is, of course, that first things first, this will torque into the orientation where like poles are the same, but that's not the end of it. They attract as well. And that's just because of the non-uniformity of the field. So first, it'll torque the normal into the point with the field, and then the net force will bring them together. Okay? So that's all there is to it. So if someone asks you ever, why is it that like poles attract? You can say, well, the magnetic dipole of one wants to align with the normal of one wants to align with the magnetic field of the other, and then the non-uniformity of the field causes them to actually have a force of attraction. And then they can say, what? What are you talking about? Okay, because you need a lot to understand why these things happen. That's why I talked about it last. But it all does fundamentally come from the fact that every single, we say is that every single electron is its own little magnet. A lot has to go right in order for that to be present up in our world, our macroscopic world. You have to have that, you go from the electrons being magnetic, to the atoms themselves being magnetic, to the groups of atoms to be magnetic, and then once you have things that can be magnets on our everyday level, this is how they interact with each other, okay? So again, if this was not a line like this, it would torque until it was. We learned about the torque on a current loop, and then the non-uniformity of the field causes attraction. Okay? And likewise, if you put something over here, let's say, and let's make it look like this. So the normals are like that. So the normals are pointed such that the north is here and the south is here. Well, that is not its preferred orientation. We, of course, talked about that being an unstable equilibrium, right? But, of course, an unstable equilibrium in the real world is not much of an equilibrium at all, right? There's going to be always something that takes it away. It's like trying to balance a pendulum like that, right? Yes, it's technically stable, but it's going to fall over. So what's going to happen is that this is going to torque until the north is over here and the south is over here, until the normals are aligned with the field. That, of course, is why north repels north, right? So north repels north, so that it realigns so that the south and north are next to each other, and then they attract because of the non-uniformity of the field. Okay? That's why magnetic poles attract. Okay? It's the same behavior as in current loops. Okay? So the next thing to cover, and we should have enough time here to do this, another 10 minutes or whatnot, we're going to talk about the magnetic field of the Earth. Now, if you're wondering why do they call magnetic poles north and south, it's because the original purpose of magnets was to navigate. So let's talk about why that is and how it works. So let's talk about geomagnetism. So meaning the magnetic field of the Earth. So here's the Earth. Has an axis. We call this the north geographic pole. We call this the south geographic pole. That's the axis of rotation of the Earth. We, of course, live somewhere over here, much closer to the north geographic pole. Here's the equator. And back in the long time ago, people discovered that there were these certain things that you could dig out of the ground, and you could put them on a little frictionless pivot and form what's called a compass, and they could help you navigate. Okay? So we have these little things called a compass. It's just a little magnetic piece of material. And we say that its north pole of the compass is because it helps you navigate toward the direction we call north. Okay? And the south pole points toward the geographic south. So we have that the normals point like this. You know, of course, that they point like so. And of course, once this had been used for a long, long time, they discovered, whoops, well, we probably shouldn't call this end of this material north because it points to the north geographic pole because opposite poles repel. So instead of renaming the things on the compass, we just said, well, the Earth's a big bar magnet with the south magnetic pole here and the north magnetic pole here. So that's because, of course, north attracts to south, not north. Okay? So the Earth is a big bar magnet with the north magnetic pole down here and the south magnetic pole up here. Because this opposites attract, right? Why would we say the North Pole points toward the north, or the north end of a compass points to the North Pole? That's a little bit of a mistake. So when they figured out a little bit more about magnetism, namely that opposite poles attract, they had to say the Earth's a big Mar magnet with the south magnetic pole near the north geographic pole. I say close, it's not exactly though. Turns out that there's, I think it's about an 11-degree difference. Approximately 11 degrees. The south magnetic pole, I think, is currently somewhere in very, 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 very northern Canadian territories, and it's on the move, swinging up towards Siberia. It's not even static, okay? It evolves with time. Where does it come from? Well, no one really knows that well. It's thought to be ion currents that are deep within the Earth's core. So some kind of current is flowing in there, and that caused the magnetic field of the Earth, and that magnetic field looks something like this. Draw a big bar magnet, our usual field. Kind of what the magnetic field of the Earth looks like. So if you follow a compass, either a good old regular compass or maybe the one on your smartphone, you can eventually meet all your friends here at the south magnetic pole if you follow along with the field lines. How do you know you've gotten there? Well, it has nowhere for it to point anymore because you're supposed to hold your compass in the horizontal plane, right? That's your phone tells you to hold it flat. So if I were to hold it in this room, it would point that way. And I'd walk that way until it had nowhere to point because here, the magnetic field lines go straight into the ground. So it has no horizontal component anymore. So then your compass would just aimlessly spin, having nowhere in the horizontal plane to point because the magnetic field goes that way. Okay? So that brings up an interesting point, is that the magnetic field lines come up out of the ground here, then they go into the ground here. Where we live is not on the equator. In the equator, they're relatively parallel to the ground. We live somewhere here where they have a significant downward component. The magnetic field is preparing to go into the ground. That's why it's really important you hold your compass level, because the magnetic field in this room does not really just point north, it points north and significantly downward. If you don't believe me, I have a compass that can be is mounted on a vertical pivot. So if I let this thing settle, it's hard to see, I know, because this classroom is oriented north-south. But that right there, so it's pointing like this. Let me kind of hold it in place and tilt it to the side so you can see it. It looks like this. The magnetic field in this room is pointed north, yes, but significantly downward. It's because it's preparing to go straight into the pole, and we live pretty close to that. That's actually an interesting way. If someone ever took you in a plane, blindfolded you, you have nowhere, dropped you off somewhere on Earth, you have no idea where you are, can't look around and see a kangaroo and know you're in Australia or whatever, okay? It just gave you a compass, gave you one of these compasses. Whether or not you have an upward or downward component can tell you which hemisphere you're in roughly, okay? So you're in the northern hemisphere somewhere if it has a significant downward component to the Earth's magnetic field. You're in Australia if it has a significantly upward component. Because remember, the magnetic field comes straight up out of the ground here, and it still has a significant upward component when you're somewhere near that. It's only roughly parallel to the ground when you're near the equator. Okay? So, I've already hinted at the fact that the Earth's magnetic field evolves with time. So let's talk about that. First of all, how do they know that? Well, if you go Here's the ocean. You go down to one of these deep sea vents. You go to the border of one of these tectonic plates. And you have lava, right? Or magma, whatever you call it. I forget the difference. One is when it's above ground and one it's not. So I don't remember which one. But it's hot, okay? It has lots of different types of atoms in it, some of which are magnetic. But the temperature is way too high to sustain any magnetization, so it has to get out and cool. And as it does so, those atoms will orient according to the way the magnetic field of the Earth wants them to orient, right? So what you basically have is that near the vent is a map of what's the recent magnetic field of the Earth, and then as you get further or further away, you get older things. So basically, whatever's the magnetic field of the Earth at the time that this thing is cooling, it'll stay stubborn after that once it's locked in place. And here's an interesting thing. You find in the geologic record that the normals point the complete opposite way, which means what? That's right. At some point, the magnetic field of the Earth was completely the opposite direction. The last time that happened was about 780,000 years ago. Magnetic poles of the Earth reverse. So whatever's going on there inside the core of the Earth is changing. So what's the big deal? Well, the magnetic field of the Earth is highly protective of humans. As charged particles come in from space, this is something called the solar wind. The sun belches out these charged particles. And the magnetic fields of the Earth tends to make them go into circles or helices, especially at the poles. And as these charged particles are making their circles and helices near the poles, they run into atmospheric particles and they glow. And this is called the aurora, right? So the aurora is basically this pretty light show where instead we'd have these high energy charged particles coming down to hit us, which is not a good thing. But if every once in a while it reverses direction, well, one of the things that happens when something reverses direction is that it's very weak or even zero in the switching process. It's like when you throw a ball up in the air, if it's going to reverse direction, it's got to stop for a moment, right? So what that means is that during periods of magnetic field reversal, we are more open to getting bombarded from space. Now, this is not something to worry about. This is not going to be the destruction of life on Earth. This happens recently. This is pretty often in geologic time. Humans have evolved with several of these reversals. Okay. Now, they say that you might be able to see a slight statistical uptick in the worldwide cancer rate, okay, during this time, because we're going to be more bombarded with charged particles, but this is not going to be a major calamity. And I say that because we're kind of overdue. Like, in geologic time, this is one of the largest periods of non-reversal we've had, okay? If you look at the geologic record, we're kind of on the cusp of a phase, of a change. No one knows exactly when it's coming, it's not predictable, but in geologic time, we're fairly close to reversal. You can already see large patches. There's a patch down, I think it's in one of the oceans, the southern oceans, where the magnetic field is already significantly weakening. It's kind of, when it reverses in patches. It's not all at once. It kind of gets weak in certain places and suddenly it flips all around. So there will be a period of time where if you traveled in a time machine to the future and you try to use your compass to navigate, you'd be walking exactly the wrong direction that you think you are. Okay? So a magnetic field reversal, it happens. It's not going to be calamitous. The biggest thing I think will be that it'll kind of knock out some satellite communication. So these charged particles can wreak havoc with stuff that's already kind of in the upper atmosphere and has less protection than we do down here. Okay, so let's call it a day there, and we'll pick up some new stuff next time.